So yesterday we started the derivation for finding the torque in an moving iron instrument. Okay, so let us quickly recapitulate as much as we did. We have a coil that carries the current which we want to measure. Okay, and then there is a piece of iron that can move closer or away from this coil, and when that happens, the inductance of this coil increases or decreases respectively. Okay, and now this coil attracts this piece of iron, so therefore some torque acts on this iron piece, and that torque we want to find out. For now, you forget about the spring, assume that there is no spring, because the torque or the force that is acting on this iron piece due to this electromagnet, that is same no matter whether there is the spring or not. Okay, so forget about the spring and let us find out the force or torque which tries to bring this iron piece closer to the coil. Achha. So we will use the concept of energy conservation for this derivation, and recall that electromagnetic energy in any inductor is given by half Li square. In this inductor, L is a function of the position of this iron piece, that is our theta. Now suppose some constant current is flowing, and at some moment we are in position theta. Okay, and now what is the torque at this position, at this angular position theta? To find that, let us assume that this iron piece is moved by a small angle d theta due to the attraction of this coil, of this electromagnet. So during this motion, the work done is torque multiplied by angular displacement. This is the amount of work done by this coil. Now also while this iron piece moves, since inductance L is changing, the stored energy, that is half Li square, that will also change. And the amount of change in the stored energy is given by the derivative of this function multiplied with the small change. Okay, Achha. Now next, so this much we did yesterday, and now let us ask from where these two energies come from, this work done and the increment in the stored electromagnetic energy. Definitely it must come from outside, from the source which supplies this current. And how does it come? It comes because, please note this carefully, we have a constant current flowing by our assumption in our thought experiment. Okay, but the inductance is increasing. Okay, when L theta is increasing, then the flux linkage, which is given by L into I, that is also increasing. And if flux linkage is increasing for this coil, then according to Faraday's law, there must be an induced voltage induced in this coil. Okay, so between the two terminals of this coil there will be a voltage induced. So according to Faraday's law, voltage will be induced across the coil. Now let me ask, how will...
Sir, can you scroll the page?
Yes, thank you. Now it's fine? Yeah. Okay.
Yes, sir.
Yeah. Now let me ask, how will be the polarity of this induced voltage? It will be plus minus like this, or opposite, minus plus. How will be the polarity? According to Lenge's law, the polarity should be such that it opposes the very cause which generated this voltage. What was that cause? What was that reason? The reason was increase in the flux linkage. So the induced voltage must try to drive a current in the opposite direction so that the current is reduced and so that it can try to reduce the flux. So this coil will try to drive a current in the opposite direction from outside. Okay. So that means this side will be plus, this side will be minus. Okay. For a very brief moment, when this moves by angle d theta, for within that very brief moment, an opposite induced voltage will be induced. And so you see current is entering through plus and coming out from the minus. That means the external source must be doing some work to push current against this opposite voltage. So definitely external source is doing work. Okay, now how much is that work? Okay, work, okay. First, induced voltage that will be the rate of change of flux linkage. That means ddt of I is constant, which you can write also as d theta, then L I d theta di. Okay, this is the induced voltage. Then power supplied from outside, external source, power supplied from outside, that will be this voltage d theta L theta I d theta di, d theta dt, multiplied by the current. Okay, so this is the power. So energy supplied from outside, that will be the power multiplied by time. So this dt will go away. Okay, so that's the energy. Now you can take this constant I outside, so it becomes I square d L d theta and d theta. Okay, so now we have all the different energy components individually. Now we have to use energy balance. Okay, so this is the energy coming from outside. I square d L d theta d theta. should be equal to this work done plus this increase in stored energy. Okay, notice these two values. I will copy it. Here I guess I have missed a d theta. Yeah. So this is torque times displacement, that is work done, plus I remember it is half I square dl d theta d theta. Okay, and if you simplify, you will get these d thetas are cancelled, and we have torque equal to half I square, okay, dl d theta and I square. Once again, as we previously told that this torque must be proportional to I square intuitively, now we also see that is the case here. Okay. Fine. So now some of you may ask, why are we not considering these spring, etc. Spring, what is the role of the spring here? Please notice that, I mean, this torque that we have found is because of the attraction force of this electromagnet on this iron piece, which will always be there no matter whether we have the spring or not. If the spring is not there, then what will happen? Then this attraction force will do this amount of work, which will increase the velocity of this iron piece. So this work will go completely into the increased kinetic energy of the iron piece if there is no spring. But if there is spring, then this torque will have to do some work against the torque of the spring. So therefore this work will partially go into the kinetic energy of the iron piece, and remaining part will go into the what do you call that, I mean spring energy due to the twisting of the spring. Okay, the potential energy in the spring. Okay, so that's the thing. Fine. So let us now come on the topic that torque in what was the other instrument? Electrodynamic. Or dynamometer instruments. Please recall what we have. We have a set of electromagnet which carries current If, I fixed, and there is a moving coil which carries a current Im. Okay, let me look at it from the top. I mean from here. Okay, then we have these two coils. and this you can only see its cross section, so something like maybe something like this. Okay, it will be very narrow. Okay, acha. Now let me first tell you the answer, then I will prove. The torque in this instrument is given by dm d theta multiplied with im if. What is m? Can you guess? Mutual inductance between the red and the orange coils, between the fixed and moving coils. Okay, and Im you know, If you also know. Now here we are taking a derivative of m, mutual inductance. That means definitely it suggests that mutual inductance must be a function of the angle. Which angle? Angular position of this moving coil. Okay, this moving coil can stay in different angular positions, maybe like this also. Or completely perpendicular. Okay. Now, among these different possible positions, in which position do you think the mutual inductance will be maximum? And in which position it will be minimum? What is mutual inductance? Let us first write that. Mutual inductance is flux linkage in one coil due to the current in the other coil divided by the other coil current in other coil, in the other coil. Okay, so if I, for example, pass 1 unit current here, then it will create some flux which could be like this. And then this flux lines goes through the other coil, moving coil also, and you calculate how much flux is going through that, calculate the flux linkage. So that will give you the mutual inductance between these two coils when this current is 1 unit. Okay, now we have 3 possible scenarios. Okay, look at this lowest diagram. Here, since the 2 sets of coils are parallel, then most of the flux lines that are generated by the fixed coil will also pass through the moving coil. So here we have maximum flux linkage, maximum mutual inductance M. But here in the first diagram, flux lines are like this. They go tangentially to the inner coil, moving coil. They do not cross or go through the turns of the inner coil. So they do not link. They do not link the inner coil. Okay. So here we will have minimum, possibly 0 in the extreme case, minimum mutual inductance M here. And in this diagram, when this is at 45-degree angle, we will have intermediate mutual inductance. So you see, mutual inductance varies as we change the angle or theta of the inner coil with respect to the outer coil, and that is giving rise to this dm d theta. Okay. Achha, now let me prove that formula. Again we will use conservation of energy. So we have to consider all the different energy transactions. Achha. Number one is stored energy. Stored energy, you have studied in your previous course that stored energy in a pair of coupled coils is given by half L F I F square plus half L M I M square plus M I M I F. That is the stored energy, you know. Achha. Now assume we are at angle theta, and the force of attraction or repulsion between the two sets of coils that moves the inner coil by an angle d theta, and the electromagnetic force or torque between the two sets of coils, between two coils, moves the inner coil, the moving coil, by the angle d theta. Okay, and if the torque at this position was t theta, then work done again will be t theta d theta, and increase in stored energy, will be d theta of this quantity, this long quantity. Okay, so I don't want to write it again, so let me write ES, E stored, okay, in short, ES into d theta. And now you take the derivative of this quantity. Here L, F, L, M, they are constant. Only M is a function of angle. So we will have only this last term d theta of M, IF, d theta. Again, assume for this analysis, this is a thought experiment we are doing. So we will assume whatever is convenient for us. So we will assume again constant currents IM and IF. Assume constant IM and IF. Okay, so this is the stored increment in stored energy. Now the question is where this energy and work done come from? Definitely it comes from outside. Outside means what? Outside means here there is a source which is supplying this current. There is some external circuit which is supplying this current. Here is also there should be a source, some external circuit which is supplying this current, and those two sources will have to do some work, will have to supply some energy that will compensate for this work done here and increment in stored energy. Okay, so now we have to find out those work done. Okay, again any question till now? Okay, fine. So yes, okay, acha. So notice that when this coil turns, mutual inductance changes. Acha, tell me one thing, whether mutual inductance increases or decreases. If it is turning by the force of attraction or repulsion between the two sets of coils.
So it increases.
Excellent, it increases. Why it increases? Because you can think in this way, that this red one is a magnet. Suppose this side is north, this side is south, north like this, and this orange one is also a magnet, and suppose this side is north, this side is south. Then what will happen? The torque will be such that it will try to rotate this coil so that the two electromagnets are aligned. Okay, north will be attracted by south, south will be attracted by north, and they will get aligned. They will come in this position. So here the mutual inductance was low, here it is high, so it is increasing. Okay, great. So yes.
So when the movable coil is in the horizontal position, so would there be any possibility that the force would make it vertical?
Yes, there is.
In which direction would be the direction would be the torque?
The torque will, in this diagram, it will be like this. See, north will go towards south, south will come towards north.
Okay, sir.
Okay, that's one way of doing this. Another way of doing this is, okay, that's, I'll just tell you briefly because it's difficult to do on 2D diagram. You have this, okay, see here. Here you have these currents. Okay, and you have flux lines. Now you apply your left hand rule, Fleming's left hand rule. So you will find the force acting on this side and the force acting on this side. They will be opposite to each other, and if you do that, you will get the same direction. Okay, in this diagram I cannot show you that, then I have to draw a 3D diagram. If time permits, later I will do that. Yeah, so where does this energy come from? It definitely comes from outside. Now you notice that when m theta is increasing, then mutual flux is increasing, and then the induced voltage will try to reduce this increment of flux linkage. So the induced voltage, according to Lenz's law, induced voltages in two sets of coil will oppose currents Im and If, and thus external source will have to do some work. Okay, fine. Now how much is that work? So for that, let us find induced voltage in moving coil. How much will that be? That will be given by the rate of change of flux linkage. In this case, only the mutual component is changing, so that is m theta into I. This is moving, so other one is fixed. Okay, this is the rate of change of mutual flux, I mean flux linkage in moving coil created by the current in fixed coil. Okay, this is the rate of induced voltage. Acha. And then I will write this as like this. And then that means power supplied by the source of Im, moving coil current. Okay, we are considering the moving coil. This is the voltage induced in the moving coil, and this is the current in the moving coil. So power supplied will be product of these two, d theta m I d theta dt I Im. Correct? Acha. Energy you just multiplied this with time. Achha, let me write this IF outside. Okay, that's constant. Okay, this is the energy from from the source of the moving, the current in the moving coil. Okay, Achha. Similarly, do I need to do it thoroughly for the other coil? I'm just writing directly. energy supplied by the source of fixed coil current IF. How much that will be? Anyone?
It's the same.
Same. Exactly same, because you have to replace M with F and F with M. It will remain same. Okay, so that will be same. Excellent. Very good. Okay, so that now use energy balance conservation. Okay, so this implies these two energies are coming from outside, so let me add these two directly. So this will become two times of this. Is there anybody requesting for access? Yeah, okay. If I forget to admit you in Google Meet, kindly tell me this in Microsoft Teams, because sometimes, and then I will do it, because sometimes I may not notice this request. I'm sorry for the delay. Yeah. Okay, so energy balance implies sum of these two, which means 2 IM IF. This should be equal to the work done and increase in stored energy. Okay, this is the increase in stored energy, this is the work done. So stored energy change is this, plus the work done, and you simplify it, very easy, you will get what I told earlier. Okay.
So,
Yes.
sir, if the source is constant voltage source, sir, will it not like simply decrease the current instead of maintaining the constant current? Like,
If the voltage source is constant,
like it's supplying the constant voltage. How will it
yeah.
provide extra energy?
Acha, let us think. Firstly, no, if there is a constant, okay, firstly you assume that in our derivation we are, we are assuming inductance only. Okay, so constant voltage source itself is a bit nasty, because that will keep increasing the current in an inductor. Okay, so next problem is that it's like a short circuit situation, that the induced voltage is not equal to the applied voltage. Okay, so I have to think in more detail. I request you also to think in more detail, but let me tell you one thing is that this derivation can be done in different ways. Okay, basically we are assuming a thought experiment, that what happens if we keep these currents constant and move it a bit like that. So previously I also did this derivation in a slightly different situation, where I assumed the flux to be constant. That means keep without any source connected. Source connected once and then the circuit is shorted, so flux remains constant, and with that also I get the same result here. Okay, so this in general can be done in different ways. We can give
Sir?
yes.
Sir, means even if the current is changing, can you assume that this derivation is for an instant, particular instant of time? Means for that we can assume that the current to be constant, means at a particular instant.
Okay.
Because current will be a function of time, but the torque is a function of theta. Means like that. Can
Okay,
we assume like
okay, wait. Yeah, a very good question actually. So the torque between the two sets of coils at any moment, what are the factors it depends on? From physical consideration, it depends on the two currents, the value of the two currents at that moment, because that will tell how strong the two electromagnets are and the relative position of the two coils. These are the only two factors. Okay, so physical considerations tell us that if these two things are given, then the torque will be always fixed. Okay, now we have derived it by assuming a thought experiment to make our life simple, to make our analysis simple. But this value of the torque will be same. Will always follow this equation when for any moment whenever the current is this, currents are this and angle is this. Now if currents are changing, then for any moment, as you said, for any moment find out the instantaneous values of the currents and find out the instantaneous angle at that moment. Put those values here. That will give the instantaneous torque, even if the current is changing. Yes?
Yes, sir, got it.
Okay, fine. How's the time? Okay, good time. Great. Achha, now, so what have we done so far? We have found the deflecting torque. Deflecting torque for different instruments. Okay, for PMMC we found it how much? BANI, it's here. Okay, BANI for electrodynamic. This is dm d theta im if. For moving iron, this is half Li square. Okay, and here for electrodynamic, this will be equal to dm d theta I square if Im equal to if equal to I. That means when you connect the two sets of coils in series, and that is a natural choice often. If you want to measure current, then you have one current that you want to measure. Where will you get the other current from? So why not you just connect them in series, and that will serve the purpose. Okay, so here dm d theta I square, here dl d theta I square with a half, here no half. So these are the deflecting torques. That means these are the torques that tries to move the coil or the pointer when you apply a current or a voltage. Okay, for electrostatic we also found electrostatic. What was this? And for all the instruments, spring torque that is the controlling, that we call the controlling torque, is given by spring constant multiplied with the angle of deflection. Now, to find the deflection, to find the position of the pointer where the coil or the pointer will settle down finally, what do we do? We use torque balance under equilibrium. That means when the pointer is not moving anymore, so that means it's not accelerating, and if it is not accelerating, then the net torque is 0, and net torque 0 means spring torque or controlling torque K spring into theta must be equal to the deflecting torque which will have different expressions for different instruments. And this is your homework to find theta for different instrument types. And to calculate sensitivity. What is sensitivity? This is a measure of how sensitive the instrument is. That means how much deflection we get, how much observable output we get per unit quantity that we are measuring, voltage or current depending on the instrument type, voltage or current. That is your homework. You can do it. Any question so far? Then I will take up a slightly new topic.
Sir, where you mentioned in one list all the instruments and their torques, can you also mention there about if it is used in AC measurements or DC measurements?
Yes, good point. Thank you. Okay, you also have to assist me in this. So PMMC, this is used for?
So DC.
DC only. We can make modification, we will make modification later. Basically we will put some rectifier circuit, then you can measure also AC. But on its own it can measure only DC. Acha. Electrodynamic? Both. DC and AC. Very good. Acha. Electrostatic? DC. In AC there will be a small problem. The problem about the capacitance of the thing, and mainly this is not used in normal in the day-to-day laboratory that we have. It is used mostly for high measurement of very high voltage. Okay, so DC, AC I will not write at this moment. Okay, AC, before I write AC I will give a thought to this. Okay, acha. MI, in principle,
AC.
Right. Actually, in theory, I mean only if we consider the physics of the attraction, etc., repulsion, etc., then it can measure both DC and AC. But when we consider the engineering side also, I mean the retentivity issues, etc., then we do not use for DC. Okay. But in theory, I mean, from the consideration that if you pass DC current, what will happen? This will still get magnetized. This will still attract this iron piece, and the pointer will deflect. So you will get deflection, and more the current, more will be the deflection. Everything fine. But from the consideration that the retentivity, which can create problem when you measure one value, after that you measure a different value, and the next value is affected by the previous measurement. So from that consideration, moving iron instruments are practically never used for DC measurement. In fact, electrodynamic instruments are used for both DC and AC. Let me just tell you a small fact, you don't have to remember this. Electrodynamic instruments are also called transfer instruments because it can measure both DC and AC. So we can calibrate this instrument by passing known DC currents. Okay, so thereby we can calibrate the scale of this instrument using DC current, and then this instrument will be able to measure AC as well. And then next, if you want to calibrate a MI instrument, you cannot pass DC current because it doesn't work properly with DC currents. So there you have to pass AC current only. And then how will you calibrate? Then you compare the reading of MI with, this is one way, you compare the reading of MI instrument with the reading of an electrodynamic instrument which is already calibrated. Okay, so that's why these electrodynamic instruments are called transfer instruments. This helps in calibration. Okay, by the way,
Sir?
Yeah.
Sir, means if electrodynamic instruments can measure both DC and AC, why do you use the other instruments? Means the sensitivity of electrodynamic instrument is also good, means it is dependent on I square. Then why do you use the other instruments?
Firstly, okay, so this is a good point. If we compare the sensitivity between PMMC and electrodynamic, PMMC is much more sensitive, particularly in low values of current. Okay, more sensitive than electrodynamic, particularly for low current. Because as you rightly said, for this sensitivity, the deflection depends on I square. So if I is very small, I is closer to the lower value, then deflection will be small here. But here, even if I is small, B is constant. Flux is always constant. So even for smaller I, it will give a significant deflection. But in this instrument, if current is low, flux is also low, and deflection is small. So dynamic instruments are not good for measuring low currents. Okay. In fact, that is why we often make AC ammeters using a rectifier and PMMC instrument. Okay, rectifier means convert AC to DC and then measure using PMMC instrument. So this is definitely more sensitive than electrodynamic. Achha. Now comparing electrodynamic and MI, yes.
So can you explain once more why PMMC is more sensitive in for small currents.
Okay. In PMMC, and electrodynamic, so we are comparing the sensitivity. In PMMC, torque or deflection, of course, let me write PMMC here. So it depends on two factors. Number one, current and flux. Here also it depends on current and flux. But for PMMC, this is a current multiplied by constant flux, because we have a permanent magnet. But here we have this current multiplied by the flux, which is also a function of the current, proportional to the current. So if current is low in electrodynamic, then both of them are low. If for low current, so let me write here, for low current, here this is constant, this is not changing, only this quantity is going down, so it will be low. It will be, if I write it low, then here this will be low, this will be also low, so together it will be very low. Okay, so for lower values of current, PMMC is better. Yes, Saurabh?
Yes, sir. Yes, sir. Got it.
Okay, yes.
So we are neglecting the spring energy just because d theta square is neglected, right?
No, in our previous torque derivations.
No, in energy balance equation.
Yeah, in energy balance. So in energy balance, we are assuming a thought experiment where there is no spring, because we want to find the torque that acts between these two sets of coil. Okay, and that torque is always same, no matter whether there is spring or not. If the spring is there, then that will add an opposite torque on this moving coil also. But if that is there or not, the torque between these two coils are always same. Okay, so to measure, to estimate this coil, I need not consider what happens when the spring is there. You notice what I did.
Okay, sir. Yes, sir. Got it.
Okay, fine. Yeah, okay, great. Save. Okay, fine. So let us come to the dynamics of these instruments. Next topic. So we have learned about the deflecting torque, this is the torque that tries to move the pointer. We have learned about the controlling torque, spring torque, that tries to oppose the motion. Okay. Now, if these are the only two torques acting on the coil or the pointer, then we will be in trouble, because what happens? Just let us consider any one type of instrument, maybe PMMC, and here we have the coil, and the spring, and suppose it is, suppose the deflecting torque is like this. Let me write TD in short, TD, and then the controlling torque TC will act in the opposite direction. Now at the beginning, at the neutral position, wherever that neutral position may be, it may be here or it may be in some other position. At the neutral position, TC is 0. Spring torque is 0. I mean, that is what we call as the neutral position. Okay, and then suppose we pass some constant current, so we get a constant TD, and then the coil starts to move, and as it moves, spring is twisted, and more the spring is twisted, TC increases, controlling torque increases. So assume this scenario, assume TD fixed, that means current fixed, and coil twisting, I mean the moving system, I mean the spring twisting actually, rather. Spring is twisting, that means TC increasing. So what will happen? This is fixed, this is increasing. At some point, both of them will be equal. Okay? But will this coil stop at that position? It may not. So when these two becomes equal, when TC becomes equal to TD, then no further torque, then no torque. But by that time, the coil might have gained some velocity, and due to that velocity, due to the kinetic energy, it may continue to move. It will continue to move due to its inertia. Okay, so coil will continue to move, and then what will happen? TC will increase. TD is fixed, so now TC overpowers TD, so there will be a net torque in the opposite direction, and so the coil will decelerate, and at some point it will stop, but at that point TC is more than TD, and therefore it will start to move in the opposite direction, and in this way the coil or the pointer will oscillate around the equilibrium position. Okay, equilibrium position is the position where TD is equal to TC. But then this is very disturbing. We are trying to measure some current or something, and the pointer is oscillating. How do we measure it? How do we take reading? Okay, so these two torques alone will not make the instrument work properly. So,
Sir?
yes.
Sir, means when the coil will start moving, when it gains some velocity, there is magnetic field, so there will be some induced EMF also, and so for this there will be some extra means torque also. So will that not be considered?
That is the next topic that I will talk after this. Exactly. Thank you for giving the clue to that topic. Very good. Okay, so hold on to that. Yeah. So right now, what I just said that this will cause oscillations, and so we need to stop oscillations. And how do we stop oscillation? We need some dissipating force, some sort of friction, some something like that. Okay, so we need what we call damping. So we need to damp out the oscillation. We need damping, and for that we need damping torque. Some sort of frictional torque that will take out the kinetic energy stored in the moving system and make it stop at the equilibrium position. Okay, so we need damping torque. Let me write T damp. Okay, fine. Next, let me give you an example of a damping torque. A very simple situation. Suppose you have a pendulum so suppose you have a pendulum and you let it oscillate. I mean, you pull it in towards one side and leave it, then it will oscillate. It will oscillate for a long time. But now if you do the same experiment with the bob of the pendulum inside water, then you should do this experiment at home. Then you will see that it stops quickly. Possibly it will not oscillate at all. Okay, so that is a kind of damping action coming from the viscous drags of water. Now, in this case, the viscous drag, viscous force or viscous drag, what is the factor it depends on? Do you know? This
velocity of the bob.
Excellent. So it depends on, and often we say it is proportional to the speed or velocity. Okay, so therefore in our instruments, the damping torque that we need, we would like to have that proportional to the velocity or the speed or angular velocity, that is d theta dt. Okay, so let me write the other two torques. Controlling torque that depends on, that is proportional to the angular position, angular deflection theta, and the deflecting torque, it depends on the current or the voltage applied. Okay, so there will be these three types of forces that we need. This is the third force, damping torque. Okay, now how we achieve this damping? Okay, I wish I could show you a demonstration. Maybe we pause for 3-4 minutes. I'll go to the lab and see whether I can bring instruments. So meanwhile you can have a short break. Okay. So this is actually a moving iron instrument, but its actual construction is not, as I told you, it's not as simple as we studied. But that's not the point at this moment. You'll notice here is the pointer that moves along the scale, and the coil etc. is actually underneath, which here is the coil actually, if you can see. But Behind this pointer, there is something like a vein. Okay, this look at here. Okay, there is a flat plate-like thing, a vein. So what happens when this pointer moves? This vein also moves, and it is I mean, it has to move against air friction or air viscosity of air. Okay, so against air friction it has to move. So this is called aerodynamic damping. Okay, so when it tries to move, this vein will get opposed by the by air, and normally this I mean this chamber that you see, that was actually closed. Now the cover is lost, so that is actually closed, and then when it tries to move inside a closed chamber where air cannot flow much, then that imparts more aerodynamic friction or damping compared to when it is open. Damping mechanism. This is one type of damping mechanism which we call aerodynamic damping. Okay, fine. Achha. So now let me write the equation of motion. Okay. So what are the forces? We have deflecting torque. Okay, that depends on the current or the voltage. So let's take one particular case, maybe PMMC. So this is BANI for PMMC. For other instruments, this equation will be different for PMMC. Okay, we also often write this as G times I, because B, A, N all are constant, so we use a common constant G, and G is called galvanometer constant. Galvanometer constant. Okay, so TD is G times I. Achha. Next, controlling torque, that we know is proportional to theta, and we will write K spring times theta. Okay, but to be more precise, I will write it as this. So this implies that this torque acts in the direction opposite to the direction of deflection. Okay, that's also true. Next, T damping, as some of you have already pointed, that we would like it to depend on the speed of the moving system, coil, pointer, etc. Okay, and so let me put a constant. Let me call it K damping constant, and to be more precise, I should put a minus sign here. So this indicates that the torque, damping torque, always acts in the direction opposite to the velocity. So that is natural. I mean, even if you look at this pendulum water experiment, if the pendulum is moving towards the left, the force is always towards the right, and vice versa. Okay, that's why this minus sign. So let us now write total torque that will be the sum of these three, that is TD plus TC plus, yes, you have a question, Ashish? Plus T damping is, okay, TC, so this should be equal to what? This should be equal to the acceleration, in this case angular acceleration, dt2 multiplied with moment of inertia. Okay, J is the moment of inertia. Okay, fine. Achha. Now let me put the expressions for this individual torques. So we will get here Gi plus, this is minus K spring theta plus, no, minus K damp, let me use shorthand. You know this, na? This is equal to J times theta double dot, second derivative with respect to time. So let me arrange it. So I will get something like J theta double dot plus K damping theta dot, this plus K spring theta plus G equal to Gi, correct? Yes. Now our purpose here is to solve this differential equation, okay, given some current, and predict how the pointer will move. Okay, so why that is important? Because we want to make sure that our instrument is such that our pointers do not oscillate too much, so that we cannot take the reading, or it does not take too long to reach the final position, so it should be fast also. So that's why it is important to analyze such a differential equation. And in our previous signals networks course or some similar course, you must have studied how to solve such a differential equation. Okay, and now you assume, suppose I is a step function, like this. So that means you have applied a current suddenly, and then we have to, so this is I versus time, and now we want to ask how the pointer position theta will change as a function of time. Will it change very slowly like this? Sorry, like this? That's not good. Or will it oscillate for a long time and then settle down? Neither that is good. Or will it go fast enough without any oscillation? So that is our question. And you all know that this is called, this oscillatory response is called underdamped response. This one is called overdamped response, and somewhere between these two we have what we call the critically damped response. That is the situation when the pointer reaches its final value in the quickest possible time but without oscillating. Okay, and you all are expected to know how to solve such a differential equation, although you, since you are from different backgrounds, you might have studied it is in different ways. That is up to you. You may use Laplace transform, you may do it directly in time domain, no problem. Okay, but finally you all know that whether it will be underdamped or overdamped or critically damped, that depends on, so damping or response depends on this factor, root over the square of this thing, k damp b square minus 4ac j k spring, and we know that if k damp square is less than 4j k spring, then this factor, or basically the roots of the characteristic equation, will be complex and we will get oscillation, underdamped response. If this factor is much larger than 4jk spring, I have to lift it up. Then this is overdamped, and the best case is when these are equal. Critically damped, but it's not critical in a negative sense. It's not that, it's good, it's something good. Okay, fine. Any questions so far? No. Okay, fine. Acha. Now we will take up a topic which one of you have already pointed out. That one. Okay. This topic I will call, people call eddy current damping. So we have seen one mechanism of damping, which was the aerodynamic damping, which to realize damping in measuring instruments. Another mechanism of damping is eddy current damping. Okay, this is like this. So remember PMMC instrument, north, south, we have a coil, let me draw only one turn. It carries current, okay, and also let me draw the top view. I may need it. Hello? Is everything okay? Connection?
Yes.
Yeah, okay, great. Fine. Acha, so now we also had a frame, okay, on which this coil is owned. Okay, you recall that? So we had a frame and we said that it could be made up of aluminium. So let us take an aluminium frame, which I am drawing like this here. Okay. Achha. Now flux lines are like this from left to right. Okay, and current is flowing in this way. Okay, now let us try to find out the direction of the forces. Okay, to find the direction of the forces, I have to use my left hand. Okay, here is my left hand, and so this finger is pointing towards the magnetic fields. This finger is pointing down along the current. So my thumb is pointing outwards from the board. So here the force will be outwards towards me, perpendicular to the board. But now here, this is the direction of flux, and current is difficult. Okay, like this, upwards, current is upward, flux is towards the right, and my thumb, which you cannot see because it is pointing into the board. Okay, so here the force is towards me, here the force is away from me, something like this. Okay, so it will move in this direction. Now the moment it starts to move, then this coil as well as this aluminium frame, they are conductors and they are moving inside this magnetic field. So as you rightly pointed out, now there will be some induced EMF in these conductors which are moving through the magnetic field. Okay, fine. So now let us find out the direction of that induced EMF. Okay, so the direction of the induced EMF, to find that now I have to use my right hand. Okay, so here at this point the motion is outwards, okay, and the flux is towards the right. So my middle finger is pointing upwards. So this is the direction of the induced EMF. Induced EMF. In the same way, if you do the analysis on this side, you will get the induced EMF in the opposite direction. And this was force. Okay, fine. Acha. So this EMF will try to pass a current in this direction. So this will be the direction of the induced current. this current will flow through this aluminum frame also. This will also flow through the coil, because the coil is also connected, it's closed outside. So through the coil also there will be some induced current due to the motion, and in the aluminum frame also there will be this induced current. Now this induced current once again will create some force, because now this current is flowing inside magnetic field, and to find out that force, okay, I have to again use my left hand. So to find that force, now again this is the, on this side I am calculating, left side, this is the direction of flux, current is upward, and my thumb is pointing into the board. Okay, so you do this experiment yourself. So that will result in a force. Okay, so this force goes into the board on this side. This is the force due to induced current. I mean the induced current. We call this current as eddy current. So let me just write eddy here. And on the other side, the force will be, of course, in the opposite direction. Okay, so these are the forces due to induced current. And these red ones were the force due to the actual current that we were measuring. Okay, so these are the force. Due to current being measured. Okay, so what do we notice here? We notice that the force due to the original current was trying to move it in this direction. Okay, so the coil will start to move in anti-clockwise direction. Okay, so this will be the direction of motion.
Sir?
Yes.
Sir, will the eddy current flow only through the aluminum frame or through the coil as well?
Both.
So then won't it affect the original current reading?
Just hold on to that question for please remind me if I forget. Okay, just after this.
Okay, sir.
Yeah. Okay. So this is the motion that is set due to the original current, and due to that we saw that the coil starts to move, EMF induced, and induced current flows, and that again causes some force, but that force is in the opposite direction. Okay, so that force is in the opposite direction. So this is the force due to eddy current, force due to eddy current. Okay, so we get a force. Okay, so this eddy current force is in the direction opposite to the motion, just like viscous drag, just like damping force, this is also in the direction opposite to the motion. Now let us also check whether this force is this force proportional to the speed. Then that will be exactly like viscous drag. Okay, exactly like a damping force. So for that, let us find out the amount or value of this force. Okay, so the value of this eddy current damping force due to former means frame, okay, due to former or frame, we will find it out. Okay, this frame is called former. So the eddy current will, as I just said, eddy current will flow in both in the former as well as through the coil. The derivation will be exactly similar. So I will do for one, the other will be your homework. So I am doing this for the former. Okay. So so let's assume that, speed, angular speed I mean, is d theta dt. Then how much will be the induced EMF? Induced EMF in former, induced EMF in one side of the former, frame, that is same as the rate of intersection of flux. Okay, that means in this top view, this coil is rotating at a speed of d theta dt, and we have flux lines and the flux density here, suppose that is B. Flux density. Okay, if that is the flux density, then at what rate this side of the former is intersecting these flux lines? Okay, so let me do that. Speed is d theta dt. This is the angular speed. Now if I multiply this with r is the radius of the coil, that means from here to here. If I multiply this with r, that will give me the linear speed, that means how much it moves per unit time. Okay, and then if I multiply this with the length of the coil, length is this length. Okay, that tells me how much area this side sweeps per unit time. Okay, so this is the area swept per unit time by this side of the frame. Okay, now this area, if I multiply with the flux density, so that is the amount of flux that this side has intersected per unit time. Okay, can you visualize that? So this is the rate of flux intersection per unit time by one side of the former. So this is the EMF induced according to Faraday's law. Now total EMF. Total EMF will be how much? We have two sides, one side here, another side here. These two sides, and their EMFs will be additive in nature. So multiply this with 2b r l d theta dt. Now 2 into r into l, that is the area of the coil. I mean 2r is the diameter, length is this, that is this area, which we also previously wrote as A. So A into B into d theta dt. This is the EMF. Okay, so now eddy current, informer, eddy current informer, that will be A into B into d theta dt, that is EMF divided by R. What is R? Resistance of the former. Resistance of former. Some constant, whatever it is. Okay, so this is the eddy current. Call it IE in short. Achha. Now this eddy current is again flowing circularly like the coil current, and therefore this will again create a torque. How much that torque will be? Since we already know that when current I flows through this coil, the torque is given by here BANI. So eddy current torque, eddy current torque, that will be BANI. That was the formula I am writing. Now I in this case is this eddy current, okay, not the original current that we are measuring. So let me write IE, and N, what can I put in place of N? Any suggestion?
1.
Yes, yes.
1.
Excellent. 1. Because of the former, the frame you can think as a single turn coil. Excellent. Very good. 1. So this is equal to BA. Let me write these quantities now. Acha, it becomes A square, D square, d theta, dt divided by the resistance. So you see, this is a constant multiplied with d theta dt. So this force is actually proportional to d theta dt and in the direction opposite to the motion velocity speed. So this is exactly like a viscous drag, and this also helps in the damping action. Okay, fine. So now next, so here the analysis we have done for the eddy current in the frame. Now your homework, do the same analysis for eddy current in coil. So what are the things do you think will change here finally? Suggestions please.
Sir, N will change.
The number of turns.
Number of turns will, so there will be so N will come in this picture. What else will change? What about this?
Area.
Area will almost be same because I mean, although I'm putting
Resistance.
resistance will change. Excellent. This resistance will change. Okay. Which resistance you will use? Resistance of
Total means total coil, total turns.
total turn. I mean this coil resistance.
We will use the reluctance.
Yes.
We will use its reluctance, right?
Please repeat.
Reluctance.
Reluctance? No, not reluctance. Resistance only, pure ohmic resistance we are talking about. Okay, so in case of eddy current informer, we have to take care of the coil resistance, but also the resistance of the circuit that is outside, whatever is there. Okay, there is definitely some source, something which is driving this current that we are measuring. That resistance will also come. So here we will have coil resistance plus external resistance. They are in series. Okay, so that is your homework. Do the same derivation with the coil into in your consideration. Achha, now let me answer the question that Amritaksya asked. His question was, there is an induced current in the coil also, and then that means that will superimpose on top of the original current, and therefore we will be actually measuring not the original current but the sum of these two currents, right? That was your point?
Yes, sir, exactly.
Okay, very good. But now the thing is, when the pointer gets settled at some position, okay, I mean it will oscillate, it may or may not oscillate, but finally it will settle down at some position, and when it settles down, then the velocity is 0. And if velocity is 0, induced EMF is 0, eddy current is 0. So at that moment we know there is no eddy current. So at that moment, whatever reading we are getting, that is definitely only due to the original current. Okay, so once the pointer settles down, the effect of eddy current and the eddy current itself is gone. So no error will come in the measurement due to this. Eddy current plays its role only during the motion, which is a helpful, good role. Okay, so that sounds reasonable.
Sir, means even if there is some eddy current, we can calibrate always now. Means if we pass some current, we will get some angle. Then we will pass some more current, we will get another angle. So we can calibrate the instrument like that only now, even if some eddy current flows. So will that be a big...
The first thing is there won't be any eddy current once the pointer settles down. Okay, so we don't need to do any calibration, because we will take the reading after the pointer settles down, and at that moment there is no eddy current, because pointer is not moving, coil is not moving, so there is no induced EMF, no eddy current. So there is no correction at all is required. That is the beauty of this thing.
Yes, sir, got it.
Okay, so I think this is a good time to stop today. And if you already have visited our course website, then you already know, or else let me tell you, we have some reference books suggested, and also some study materials. I mean, which sections, which chapters to study for different topics, that is also suggested. And today we have completed our first chapter, which is not the first chapter in our book. I don't remember the exact chapter number. It is written in our website, in our web page. So you see also some practice problems are given, problem sets are given, and for many of those problems answers are also given. All the answers may be wrong, I may have mistakes. So you should practice at some, and also the dates of major class tests are announced, tentative dates. One is at the end of January, one is at the end of February. So you should prepare. Since last time you compelled, I took so many tests, so I decided to honor your opinion. This time I will take only 2 tests. Professor Devashish Mondol will also take some tests. So, but from my side, only 2 tests. So have a look at the web page, please. Okay. Any question? Any technical, logistical question?
Sir.
Yes.
Sir,
The yesterday's lecture is like, is it uploaded on the YouTube page?
Yes, it is uploaded.
Yesterday's lecture.
It is already uploaded. And the link for the YouTube channel is also there in the web page. I mean, this board works up to yesterday is uploaded, and the link is also there in our web page. Yeah. Anything else? Okay, thank you all. Bye.